Hello guys, welcome back. So in this video we are going to see the depth first search in graph, right? So we have already seen the graph traversal, right? How to do the graph traversal, right? But I have done in the BFS that we have seen in this class that, and so in the graph traversal, right, we can do graph traversal node by node by either BFS, right, or either we can do DFS. Okay, so breadth first search is doing by level, and DFS is going by one node, one of the node it will traverse and will go to its all children, will not go by the level and level, right? And if you remember the tree, we are going with the level by level tree, right? Like if we have a node like this, right? Let's suppose this is parent, this is child nodes, right? So first we will go with the first level, then second level, then third level, 0 1 2. These are the levels, right? So in the base first we will traverse all this level, then this level, and then this level, right? But in the DFS we will take from here, we'll go here, right? So we will traverse all these nodes, right? And then we'll move to here. Okay, so so the graph traversal, right, we have here is BFS and DFS, right? So BFS is nothing but breadth first search. You can say breadth first search. Okay, and in the DFS you can say depth, name says, right, depth first search, right? So breadth first search and depth first search means BFS and DFS we will do through Java code, right? And we will provide some illustration also that will help you to understand, right? So first of all, let's understand the what is the algorithm for this, right? So what we will do, we'll start with one of its you can say source node. Let's suppose if we have graph, right, like this. Let's suppose this is your graph. Okay, so we'll pick one of the node. Let's suppose we'll take this node, right? And then we'll uh, uh, let's suppose we will say this is a source node, right? This is source node, right? So we'll start from the source node and we'll mark it as visited. If it is visited, we'll mark it. Okay, then we will move to its children. Either we'll go this side or this side. Once we will go here, we will mark it. We are already visited. So this is visited, then we'll go here and we'll say this is visited, right? Again we'll say which is not visited, either will come from here or you can come from this side, right? So you will see this node, it is visited, we will mark it. So why we are marking it? So that the loop will not continue in infinite loop, right? So we'll take one of the start node from the source. You can say we'll start from the source node and we'll mark it as a visited, right? And we'll to mark it visited, right, is it visited or not, right, we will take a queue, right? We'll take a queue like this. Okay, and we'll keep all the details there, right? So we will use this queue and we'll keep track of the nodes to be explored. Which node we will going to explore? Let's suppose this is 1 2 3 4. Let's suppose we'll start from 1, right? This is marked, right? So what we will do, we will mark it that it is already explored, right? So this is done. Next will come 2, this is done. Next 3 will come, done. 4 will come, next done. Like this we will do, right? Means we will use a queue and we'll keep track of the nodes to be explored. Okay, now what we should do, we will in queue all the queue one by one, right? From the source. Let's suppose we have put the source here. When we do in queue, means we will remove from here. So we will traverse 2 children. We'll see, oh, we have 2 neighbors here, right? Let's visit this. So while the queue is not empty from this queue, what we will do, we'll get from the queue one by one. Like let's suppose first 1 we will take, then 2 will take, like this we will get until it's not become empty. And then we'll put from the front queue. What we will do, we'll dequeue a node like this node from the front of the queue, because this is the input and this is the output, right? So from the front we will dequeue it, means we will remove from the queue. The removing from polling from the queue we can say, or dequeue from a queue, we can say, right? We will dequeue a node from the queue front of the node from here. And what we'll do, we'll process the node, and if you want to print it, if you want to record it, you can do that. Either what you can do, you can add all the nodes somewhere. You can also add, right? You can record it, you can say, right, in the list or somewhere, and you can return all the traverse one. After that, what we will do, after the enqueue all the unvisited neighbors that is not visited, right, of the node that we will dequeue, we will mark them as a visited, and we'll put it into the record where we want to record it or want to put it, right? So I hope you understood what we are going to do, right? So let's start implementing here, and I hope you will enjoy this video. And if you are already aware with BFS or DFS, right? So we'll see that. Okay, so we have already talked about the BFS, right? So that we are talking about, but when we are going to DFS, right? So in the DFS, what we will do, give me 1 second. So that is a part of BFS, right? But when we are going to do DFS, what we should do here, right? So first of all, let's suppose we have a node like this, right? Like this we have, right? So what we will say, this is your start, this is your source node, and we'll mark it as a visited, right? Let's suppose 0, 1, 2, 3, like this, right? We can say. So we'll mark it as a source node, okay? And we'll start from here, and we'll say mark it as a visited. Once it is visited, we will we can take a queue also, or a stack. So in the DFS, we'll take queue, right? Because we are doing a recursive, right? So when DFS means recursive call only, right? When we are talking about the DFS, means we'll do recursive call. If you are aware with the recursive call, means nested call, you can say, right? Means the function will call itself. If there is M1 will call itself. Let's suppose M1, like this, right? So this is called recursive. Okay, so same thing, the DFS will work, right? So we'll take a stack to maintain the stack. We will take a stack here, right? This is your stack, and what we will do, we'll keep track of all the nodes to be explored, right? Like we are doing for the queue in the BFS, right? Similarly, we'll do here for the DFS, right? Then what we will do, we'll push all the source here. Let's suppose source is 0. We'll put this node here into the stack, and while the stack is not empty, what we will do, we'll remove from the node, right? So like this we will remove. Okay, so once we will remove from the you can say top of the stack, then we will proceed this node, right? Let's suppose we'll do pop, and now current node is 0, right? So we can store somewhere this is visited, or we can take in the list also, this is visited, let's suppose. Okay, so this is done. Now we'll push all the unvisited neighbor. So its neighbor is what? Give me 1 second. Its neighbor is this one and this one, right? Either will go like this or this, right? So 2 neighbors is there. So we can put all these neighbor here, 1 and 3 will add here, right? So this is not null, right? We have already removed here. This one is already removed. Now in the stack we have what? 1 and 3, right? So on the top we'll remove from here, 3 we will remove, means we will mark it as a visited. So 3 will come here. So this is also done. So this is done, right? Similarly, we'll remove now this is not here, only this one is here. We'll put 1 here and we'll mark it as a done, right? Means we can store it also, or we can mark, we will mark it, right? Because this is visited. Like that we will push all the nodes, like we will put 2, or if there is more nodes are there, so we'll push all the unvisited nodes, or you can say neighbor node, onto the stack, and then we will mark it as a visited, right? So that what will happen, you will have all the details on the stack, that is it visited or not, because we are putting on the stack, we are removed from there. So you can store it somewhere, or you can keep printing this one, Either you can store it, or you can store means record. Either you can put into the list of list, or you can store in the somewhere, or either you can print it, right? So let's suppose let's go with the implementation first. We'll do implementation and then we'll talk about the time complexity and space complexity things. We'll talk. So what we are going to do here, first of all, so we'll take some graph related things, right? So we have already created the graph, as you remember here, right? This graph. So I will not go much deep here, but I'll keep adding some simple things here, right? How we are going to do simple things? We will not add more things here, but we'll do we'll take a, let's suppose we'll take a map here. Okay, what I'm trying to say, we'll take a map, like we'll take integer, and you can take a integer, right? So each node contains a list of neighbors, right? Each node will contain a list of neighbors, so that what we will do, we'll take a list of you can say integers, right? Means neighbors. As you have seen, right? Because what we had one let's suppose what I'm talking about, we had this 0, right? We had this 0. This 0 have two neighbors, so we'll keep like a map of 1 and 3 like this, right? So I have a list, right, that contains 1 and 3. So in the map, let's suppose what is this? This is a map. Okay, map at some value here. Okay, at 0 index. At 0 index we have node 0. At node 0, if we'll find, we will get 1 and 3. So we are going to write what? Integer here, integer, and then we'll add list of integer, right? I hope you understand, right? Now we'll say this is nothing but your graph, right? And we'll say new HasMap like this, right? We can do, and this is key value, we can remove it. Okay, I can see I have imported HasMap here, list and map, right? All these three things we have. Now think what we are going to do here, right? So we have already created a graph HasMap, and then I will put what? All the nodes here. Let's suppose we'll start from putting let's suppose we'll start from 1. If we have one node, right, and the node first, this is source node. Source nodes contain a list of, you can say, node. So I'll go with arrays dot list. As you remember, we can add multiple values here, right? Multiple neighbors here, like this we can say. Similarly, what I will do, so I'm adding all the nodes here, right? Neighbor nodes. So what I'm trying to do here, now I will put we can take 2 here. I'll add 1. 2 is connected with 1. Then we can take let's suppose 4 and 5. Okay, similarly we can add more thing. Okay, let's suppose we have 3, and 3 is going to connect with it will connect with 1 and 6, right? Then similarly, okay, like this I have added 2 more. Now let's suppose we'll go with the 4. So 4 will connect with what? Let's suppose it will connect with only 2. Okay, then we'll take 5, right, and we'll connect with 2 only. Similarly, we'll have 6, and 6 will connect with 3, right, like this. And let's remove this one. So how we have created this? Let's see, give me 1 second. So here, if you observe this, right, so if you have observed this code, right, what I am doing here, right, first of all, I have created a node 1 here. I'm talking about this line. So I have created a node 1, and this is your source node. Let's suppose this is nothing but your source node, and this source node is connected with 2 nodes. It has 2 neighbor nodes. The first neighbor node is 2, another I'm taking what? 3, right? So this line is completed, line number 12. Now I'm going with line number 13, means 2. So 2 is connected with 1. It is already connected with 1. Then it will connect with 4 and 5, right? So I will connect with here 4, and it is connected with 5, like this. Okay. Then 3 is connected with 1 and 6. 3 is connected with 1, and there will be a 6. Let's suppose I'll take 1 6 here, like this. We are not giving arrow. Don't think this is arrow I'm giving. So there is no arrow, okay, because this is not directed graph. Then this is done. Now think about 4. 4 is connected with 2. 4 is connected with 2. It is already connected. Let's suppose now we'll go with 5. 5 is connected with 2. That is done. 6 is connected with 3. Okay. So this is done. So this is your graph that we are talking about. Okay. So this is your source, and rest of the thing is like that. Okay. So graph is doesn't mean that it's a you can say closed one. It should not be closed like this. It can be closed or it cannot be closed, right? We can say. So that is why I have taken like this. Okay. Like this. So this is our graph that we have created. Now let's go to the further in the line of the code. Okay. Now what I want to do, I want to create a visited node, right? To create a visited node, what we should do? Think, first of all, I'll take a set, right? And set is nothing but list of integers, right? Integer, like this, right? This is the set. I will say it as a visited, and will mark it as a some value we will put here, right? So let's suppose new hasmap will take, right? Hasset I will take like this. Okay. So we have created a visited set so that all the unique nodes will come, because see, if you see, multiple nodes was coming and it is having multiple times here, right? So we will map that, we will put again. So it should not have, it should be visited, like will not go vice versa. What I'm talking about, why we are taking actually. So see, we have created this graph, right? What we have done, we have created this graph. So if we will go from here to here and we already mark it, right? So because this is, we have already created 1 and 3 we have already done, right? So if we will already visited with this, so you are seeing here 2 is coming 2 times from which, from this one and this one. So we will have this entry into the stack, but it should be marked. If it is not marked visited, then what will happen? It will go again into the stack and it will reprocess, right? Means it will take time, and the same node we are doing multiple times. 2 will go with 1 5 1 5 and 4 3, right? 3 times it will work, right? So if we'll mark it as a visited, when we'll process here back, it will not say never node about the 5, and we will not talk about the never node of 4 because it is already marked, so it will not process again. I hope you understand, right? Now what we should do here, then we'll take a DFS, and then we'll add we'll create a DFS utility method, DFS, or you can say DFS name function is also there, right? And you can provide these things, right? So first of all, we have to provide a graph, right? Then what we will provide, let's suppose I'll start with the first node, right? You can, if you have a 0 or whatever you have here, right? You can take any of the node as a source node, right? I'm taking 1 as a source node. Then you can take visited, right? Visited. So this is the function that we are going to create, right? So how we are going to create? If you'll put the cursor here, you can create directly, or you can write here, right? So this is the function that I was talking about, right? So I have created this DFS function because we have to write this code, right? Until we will not write this code, it will not work, right? So first of all, as you can see, this is you can take public or private, doesn't matter for here, or if it is public, it's good actually. You can call outside the class also, right? So let's suppose we'll take a public static void, because we are not doing any, we are not returning anything. We can print here. We'll take some system.out.println and then we'll print. So we can take as a void, right? We are not returning anything. Then this is the map of the graph, right? This is your graph, right? So we'll keep similarly that we have taken. I is nothing but your start, or you can say source node, right? So I'll say it as start. start node you can say, or source node you can say, right? Then we have set visited as usual. Now what we will do here, right? We can create some condition, right? If it is, if the start is there, right? If node is not there, then what we will do, right? So what we will do, we'll take a first of see start is there or not. If start is there in the visited, so what we should do, first of all, checking the visited. If it is in the visited dot contains, okay, start should be here. I'm talking about if the start is already visited, right? We will not do anything, we'll return here. Okay, we will return the control because it is already visited, so no need to visit, right? That we will do. If it is not visited, then we have to continue, right? So that we'll say visited dot, first of all we will mark it as a this node is visited. To do that, what we have to do, we have to add on to the visited, right? Visited is nothing but your set, right? Means now we are saying before processing anything, we'll say let's put the source node as a visited, mark it as a visited. To do that, what we have to do, we have to add into the visited set, right? So next time if we're going to see, so line number 27 will say, oh, you have already visited, guy, do not need to process it. Okay, then let's suppose after marking is visited, I want to print it. So I'll go with system.out.println, and then we are processing the node here, or either you can store. That is why we are saying either you process the node or record it, or save it, record it, right? Like that we can say. Okay, now think what we should do. Now once it is visited, means first it is visited, if you remember this one, right? So once one is visited, we will go with its neighbor 2 and 3, right? So we will go here by 2 and 3, right? So to do that, what we have to do, we'll create a for loop, and we'll check on the graph, right? So from the graph, if we will say get, and we'll pass our start node, right? If we'll start node, so what we will get here, obviously we'll get a list of node. What we will get, you can keep alone here also. Let's suppose what I'm talking about, if we want to find it, right? What we will get here, because see, it is nothing but your list, right? Here you can see, right? This is your list. So you will get a list of neighbors like this, neighbors. Okay, okay. So on the neighbors, if you mark as a node here, what you will get, one integer, and this is nothing but your what, your neighbor, right? So I'll say from the one neighbor we can take like this is a single neighbor from the neighbors list, right? We'll get one by one neighbor here. I hope you understand, right? If you have any doubt, please ping me in the comment box. You can say in the line number, sir, I do not understand that line number 33 or like that. Okay, I'm making it's very simple. Okay, still if you have any doubt, please ping me in the comment box, don't hesitate. Now think what we have to do. Now we'll mark if this node is visited or not, right? So we'll check if it is not visited, so that we'll say not visited dot contains. If it is not visited, if your neighbor node is not visited, right, in that case only we will do DFS, means internal. We will go more deep, right? Its neighbor node will pass, right? Similarly we'll pass graph, then we'll pass, now neighbor will pass. What will pass? Neighbor, not source, right? We'll add neighbor, then the visited one will pass, right? This way we have to go internally. As you can see, this method itself calling here at line number 37. That is why it is called recursive, right? And it automatically maintains the stack because it internally creates. Or what you can do, you can create a explicitly a stack, and then you can maintain that. We can see in the next video. I'll try to create. Okay, so what we have to do here, first of all, we have to create a definition of the function, then internally it will call itself, right? Because here we were passing start, now we are going with its neighbor, means from where we have started, this was your start, one was your start right here. So when we have done DFS, internally we will provided graph, then one, and then we have passes visited, right? This thing, when we are calling this internally, now we are passing DFS, now graph will pass, now at the one we will pass 2, and then then we'll pass DFS, graph, 3, and visited. Like this, internally it will create a stack. How it will create? So first it will came what? Source, right? Source is nothing but your 1, you can say. Then it came what? 2. Then it came what? 3. Like that it will create a stack, you can say. It will build a stack, okay, and so on. That is why, because whenever we will do recursive calls, it will create a stack frame, right? And each record here is called stack frames, right? Activation record, you can say in the Java, or either you can say entry in the stack. Okay, so don't think about the words, you can say. Simply we see here what we have done here. We have created a DFS function, we are passing graph here, then start, then visited. Then what we are doing here, visited contains start, then we'll return, means this is already marked. If it is not marked, then put into the visited, print it or record it, then take a neighbor node, right? And then go with all the neighbors one by one, check if it is neighbor node is visited or not. If it is not visited, put into the call itself in the DFS method. So it will traverse to its all childrens, right? I hope you understand this video and you like this video, guys, right? So let's do some hands-on actually to understand this example. So what I'm trying to do here, see, let's suppose we have created a graph tree. Let's suppose a graph. Okay, fine. We have 1 and 2, then we have here 3, then here we have 4, and here we have 5. If we will take here as a 6 here. Okay, so this is the graph that we are talking about. We have created simply in the simple language. 1 was connected with 2 and 3, 2 is connected with 4 and 5, and 2 is connected with 1 also, and 3 is connected with 6. Okay, now what we will do, if we will go with the DFS, what will happen? I want to see how you are understanding. So internally, first of all, what we have passed, start. So we'll start with the 1. Okay, so I will start with the 1. So this is done, right? Now we have either will go in this side or either will go in this side, right? So let's start with 2. So I'll go with the 2. So after 1 we'll go to the 2, right? Then we will not go to the 3 because this is DFS. If it is a BFS, then we will go with the 3 now, but this is DFS. So in this case, after 2 we will not go here, right? We will go where we will go, means we will not go this side. Which side we will go? We'll go this side, means we'll traverse to this side. So after 2 we'll go to the 4, right? Once this 4 is done, then we'll go to 5. We will not go 3, still we will have to traverse this, right? So we'll say 5, right? Once this 5 is done, right, then we will come to here, right? Then we'll traverse to 3, and then we'll traverse to 6, right? So this is the way we do DFS traversal from the node source node 1, and we'll traverse like this. Okay, so I hope you like this video. Still, if you have any doubt, please ping me in the comment box. Okay, now let's talk about you can say the characteristics, you can say, or you can say complexity thing, or what is the complexity of this program, right? So if you'll talk about give me 1 second. Okay, let's suppose what are the characteristics of this DFS, right? So if you do order of explorations, right? So we have a DFS, right? So this DFS explores as far as down, right? As you can see, 1 2 4, then 5. If is there more kids are there, more children's nodes are there, it will go till down, right? So it will explore as far down a branch as possible before the backtracking, right? Before the backtracking, until it will come here back, it will go all its down to its branch. Okay, then the DFS will do path finding, you can say. When a DFS do path finding, so DFS does not guarantee the shortest path, you can say. It will not do guarantee your shortest path. So better, if you want to do shortest path problem and those things, you go with the BFS, not the DFS, right? So when we are talking about the path finding, DFS does not guarantee the shortest path. Okay, so it is more suited for you can say task required, like complex or you can say if there is some task, right? And we want to we require to complete all the explorations, right? We want to explore all the nodes, right? Those type of things you can do through the DFS. If you talk about here complexity in this program, right? So if you talk about the space complexity, right? So we have observed that we are storing all the nodes here in the visited, right? So I'll say if there is V is the vertices, number of vertices here, because we are saying vertices, right? So I'll say O of V in the graph, right? Where V is the vertices of the number of vertices given here, right? So due to the stack, we are doing storing here, right? It internally will do a DFS. It internally it will save into the you can say where it will save into the visited, right, stack. So it will have O of V, right? Now if you'll talk about the time complexity, okay, so you can see we are going with all its node, and then we are also taking the edges, right? So we can say O of V plus E, where V is the vertices, E is the edges of the graph, right? Why I'm saying it? Because see, if you remember previously, whenever we create a graph, right, there is always a edge between that, right? You can see here we are between the two nodes or vertex, you can say. We always when we are going to add those vertices, right, we have to pass edge, right? There should be an edge. As you can see here, we are building an edge, right? So we need the edges. Similarly, we have taken here map, right, has map, or either you can go with this one also that we have already seen. So if you have things like that, you can do that. Otherwise, just think. So there will be a space complexity of V, but we are talking about this time complexity, it will be V plus E. Okay, so thank you guys, thank you for watching this video. If you really like this video, please hit subscribe this channel, and I'll keep updating all those you can say required videos of graph algorithms. So I'll see you in the next. Thank you for watching this video.
Thank you guys, thank you for watching this video, and if you really like this video, please subscribe this channel.